Something that has served me well in coding in general is to think about what I'm doing. And sometimes when I do that, things will come up to me. As I was getting these test scores, I was thinking, wait a minute, am I testing on the right data because I copied this code? And I am not. Okay, because if you look at the function, another issue with copying and pasting code here, it's on X, and we need this to be on X train, Y train. That defeats the whole purpose of splitting the data. Okay, so I think I need to go up as well here. Yeah, here it is on. See, here the 646 is on X train and Y train, but here it's not. So these have not been appropriate bases of comparisons. And now it's even on a smaller set of the data. So these may change, right? And let's find out. Okay, we're going to run them again. So it's still got 400. And it's... now that's interesting. See, 350 is better. We're going to use that because it's less, right? Even though it's only a slight gain, if less is better, let's go with less. And we can always further adjust that later if need be. Okay. And now, so I'm just going to run through these one at a time because, right, the next line of code is based on the previous one. So we still got a max depth of 2. Wait, what is the default here? Because note that the score, this doesn't make sense. The score went up. I thought the default max depth was like 6 or 8, which means it should be giving at least the score that we got. So recall that my little trick for doing that, if you just start typing in XGB regressor, put in the parentheses, and then we see if you look for max depth, where is it in here? 3. Oh, 3 is the default. Well, what do you know? I thought it was different. I thought it was 6. Okay, so this is a good test. So this should be the case that then 3 should give us back the 638.71. Oh, except it was 400. So let's try 350. Okay. And maybe in this case, maybe I do want to try a little different. Like, hey, will it be better if I try 325? So to get back the right score, let's try something different. I guess 325 is better. Okay, so we'll just leave the 2 now for 325. Now max depth of 3 is the default. If it's the default, I can actually take it out. Although I could change it later, so it could be nice to leave it in. Okay, so sometimes this happens. You just got to go through the code one more time, and you can see like it's kind of interesting actually to see like how it's different. Still no changes. The max depth of 3, I guess, is the only change so far. And this makes a little bit of sense. The idea is that, hey, if you're dealing with less data points, you may need more like, more of a tree depth to figure it out. So yeah, the learning rate stays the same. Okay, so this is our best shot here. This got a better score before. And by the way, you can like, you don't have to like keep things exactly the way that they are. You can change them a little bit. And what I mean by that is, well, let's just run this one first and then I'll show you. I'm going to change this, okay? Because we did see some different pieces. And, well, first of all, I haven't tried like, say, 300. Will 300 do better? Did I go just too high here? Ooh, and we did get a good score. So it looks like a very similar combo is actually working. That may have, it looks like, I think it may have been a little different, but those three numbers are working well. So for instance, I could try like, now I could say, well, now let me go back to these and check. I want to put the, see, you want to put the same ones in there because different combos could work. Okay, so call sample by level is scoring optimally so far at 0.8. Call sample by tree at 1, which would be the default. That means no changes are made. And call sample by node at 0.6. And I don't think about like details of like, well, what's the difference? I just think, look, these are 3 different ways to split them. So no change, no improvement, which is good to know. That makes me feel a little more confident about the adjusted max depth in estimators. Okay. And I could also try to do more, I'm happy to continue with these, but just to show you, right, I could do more, leaving the max depth now, leaving in estimators. But I did some pretty big jumps with these other ones, right? And I can say maybe some other combos will work better, right? What about 0.7 and 0.9? And it didn't take too long to run them all. So it was, what if I try just one decimal place higher and lower in each one, right? Or you might want to even try like 1.5. That can be a little more indicative sometimes. So if I go like to 0.65, right? And I mean, it's 0.95, that might be the same. I'll leave it at 0.9. But 0. You know what? I'm going to change and keep it at 0.1 away. And maybe this one I'll just, well. See, that one you can only go in one direction, but what's nice is if you think, well, maybe I have a free one to add. What if I had, let's just try that. Okay, so we're just making little adjustments to see, can we do better than that 616.53? And then we're going to get into the other XGBoost parameters. I mean, like that's interesting, right? It's so slight. But like when you have nothing. Okay, so this one is presumably less columns. It's going to generalize better. I'm going to stick with the 0.8 here. If you were like final thing in scoring, use the 0.9. Oh, look, but call sample by node also went down. So see those two in combo. So let's try this. What if I try the call sample by node at 0.5? Leave this. And then the calls. I mean, it's already really tried, I guess, the combinations. So do I go with, see, this is the thing. Do I go with the 0.8 and 0.6 or 0.5 and 0.9? That could be something to actually revisit later since the scores are so comparable now, right? I'm going to go against what I said. Maybe just stick with the most recent. Okay, what else do we have? Well, let's put in the XGB regressor, parentheses, cool way to do it. And we can see there's a lot, as far as like general tunings that we've talked about maybe a little bit, or that we can use here. Let's try gamma, min child weight, and subsample. Okay, I'll make notes of those. So we got gamma, min child weight, and subsample. Now subsample is less rows, and that can be interesting because sometimes getting rid of problematic rows can be helpful. I tend to like to do that one by itself sometimes because it can be powerful depending. So let's just try it. I do want to get a randomized search in here, but I just kind of start to go with the flow. And so I'm adding in a new one now, subsample. And these are percentages of the rows. So again, it takes them all by default. And we want to try like I don't know, it seems like half would be a kind of extreme, right? Because I'm going to go 0.6, 0.7. The idea is, right, more data the better. So sometimes like high numbers can actually be helpful because you can think like, what if I just get rid of a couple of rows? Will that be helpful? Okay, so let's just try it and see. And I also want to look at gamma. Yeah, I didn't put in 1.0, so it did not help, right? You can see that the score went up. Okay, I want to try gamma. So gamma, if you're ever wondering, well, what? I want more info on this. Well, if you go to like I do now for gamma, if you go to XGBoost parameters, they're all here. And so this is the official documentation. Gamma minimum loss reduction required to make a further partition of a leaf node on the tree. The larger gamma is, the more conservative the algorithm will be. And very importantly, it shows you the range. Okay? So basically, the general idea here is that, when you keep splitting like trees, gamma can actually come in and say, hey, wait a minute. I'm going to set this up so that you cannot split them further, but it's based on a loss reduction, which is different than other stuff we've looked at. And the loss is based on really when you're looking at the building of the model itself, okay, is more like they call it the objective function. Like the loss has to do with, see, it's not the error. The error is kind of what you're scoring the model on. Like the loss is based on like, hey, when I'm building the model and I'm taking these random quote multipliers, I say quote because XGBoost it's done a little differently than just strict multipliers. It does different things with it. And I say, well, how well did I do? Well, you're trying to minimize the loss. It's sort of different than the error. Anyway, that's my best attempt at explaining it. I tend to look more at the numbers. I look at that range and I say, okay, let me just try a gamma with a range. Now, subsamples, I like to keep, when you're doing this, you want to keep a record of all the hard work that you're doing. You don't have to like share everything when it's all said and done, but it's good to have the record. Okay, so like keep what you're fine tuning. So we're saying, hey, no improvements there. Now let's try gamma, right? So gamma, again, 0 is the default. Now it doesn't mean that then small numbers won't be helpful. From memory, I've seen things like this. Let's just check those. Okay. Gamma did not improve, right? And the other thing is, I do want to mention that it's the further you go, like in the fine tuning process, the harder it is to find improvements because you're already doing things to try to like, generalize better to more data. Okay. And pretty soon we're going to try the fun randomized search, but let's also try min child weight. So I copy all this. I come down here. I'm going to put in a min child weight. This one I tend to forget, but I shouldn't. So we're going to go back to the documentation. Gamma, we'll leave it at 0. And the ones that are the defaults, like it could be worth making a note actually to yourself to keep track, right? Like default. And what the defaults mean is that it's still been fine-tuned because you've checked them, but note that you're using the XGBoost recommended values. Okay. All right, so what about min child weight? Default is 1. Minimum sum of instant weight, Hessian, which is a linear algebra term, needed in a child. If the child is like the next, layer. Like you split it, child. If the tree partition step results in a leaf node with the sum of instant weight less than min child weight, then the building process will give up for the partitioning. This task assembly corresponds to minimum number of instances needed to be in each node. The larger min child weight is, the more conservative the algorithm will be. Okay? So that's, I think, what's important. Because typically you want to generalize more and you want to increase it. But note the default does include 0. Okay? So let's just go up. I don't know. It can be worth going down too. You never know. Let's try it. Okay, 1's the default. So we're going to see if we can improve that. Again, we could or could not put it in there. We know it's 1 by default. So try 2, 3, 4, 6. Okay, something like that. See, without knowing much about it, if you have the range, you can actually do something with it. And look at that. We found an improvement with 3. Okay. So awesome. Okay. Let me check. So we've looked at those 3 to see if there are any others within the XGBoost regressor that I want to try now. You can see that there are a lot of others, and I can tell you that some of these are like number of threads, number of jobs. They're not really to improve the model in objective reg linear. Not really. For bossy, it's telling me what it tells you. Not really. So a lot of these are not in fact like, oh, how can I tweak this to get a better score? Max delta step is very specific. You could try some of these others, right? Just to show you, right, what the process. I'll do one more for the heck of it. Like, I might be like, yeah, what is this reg alpha and reg lambda? We'll go to the XGBoost parameters and look them up. L2 regularization term on weights. Increasing this will make the model more conservative. Oh, that's worth trying. You can see the default is 1, and it says increasing will make it more conservative. So it's similar to min child weight in terms of what you'd want to do with it. All right, let's make this the last one because I think you get the general idea here of what I'm doing. And got a cool new min child weight, an improved score of 6.11. And finally, we're going to go with the, oh my gosh, was it reg lambda? By the way, the L2 score is the Euclidean metric, which is standard, which is what we're using, like as far as the error goes. Okay, I think maybe I typed it right. And then it said 1 was the default, so we wanted to see about increasing it. So we'll try something similar to the min child weight there. See what we get. Oh, wow. Oh, and look at that. 6 got the best. Okay, we're almost cracking 600 here. So let's try it again. All right. Okay, so we got the best with 6. I want to see it again if it's the best. So 5, 6, 7. And it doesn't say it has to be whole numbers either. So let's start with that. Because, you know, whenever you get a significant gain with something, try. So we still got 6. Let's try like in between, right? It'll usually tell you if it's restricted to be integers. You know, in math, usually anything's game. So about 5.5. How about this? 5.5, 5.75. We've already seen the score for 6. 6.25 and 6.5. So I'm basically splitting data. Running it. Yeah, we did improve from the 6, but you can see it is giving different values for like different numbers. So this is currently the best, well, that what we have here with 6. And I'm going to pause here. And I want to pose like a little challenge for you. So when I run this, I get 601.97. Now, many of us have bias toward numbers, and I do that too. When I see that, I'm like, but I really want to get under 600. Like I really do. And here's my challenge to you is this. Can you actually improve, you know, this grid search? You could, I don't know, like I may or may not try like a couple more things to get under 600. So I'm going to pose this as a challenge to you. And what I'm going to look at next is how you can go back and combine like all the values in a randomized search, and then and then in conclusion, we'll look at wrapping up the final model on all the data. Thanks.